In the dim hall, chalk dust drifted as Einstein sketched two narrow slits and a distant screen, repeating Young's simple arrangement. He described lamps at first, then the new electric arcs and mercury lamps that sharpened the interference fringes into crisp alternating bands of light and dark. Each bright stripe marked where crest met crest, each dark lane where crest met trough. The pattern rose purely from geometry and timing, as if light flowed like water through the openings. Einstein's hand shifted to a second diagram, this time evoking metal plates, faint sparks, and the photoelectric effect. He recalled how sharply defined thresholds had pointed to light as a stream of localized energy packets, each quantum prying electrons from metal with bullet-like precision. He spoke of fixed frequencies, of Planck's constant, of energy arriving in indivisible lumps. No continuous wave could explain such abrupt liberation of charge from a surface bathed in radiation. Then he returned to the two slits and posed the unsettling question. If light truly consisted of quanta, each quantum should have chosen one slit or the other, like a grain of sand. Yet the interference pattern demanded that something passed through both, spreading and overlapping with itself. He suggested that energy seemed concentrated in particles, while the laws of propagation followed waves. The ordinary notion of a single solid object tracing a single path through space no longer sufficed. In the close air of the lecture room, the sun climbed just high enough to catch Young's narrow window. He checked the shutters, leaving only a controlled shaft of daylight to fall onto the small brass plate he had drilled with a pinhole. Dust drifted through the beam as he leaned in, nudging the plate a fraction of an inch. On the bench, the thin card waited at its edge, a sliver poised to divide the single, tidy column of light into two separate threads. He slid the card forward until it grazed the pinhole's emerging beam, then stepped back toward the far wall where a sheet of paper hung as a screen. Where geometry suggested two pale spots should have appeared, a row of bright and dark bands stretched across the surface. He narrowed the aperture, adjusted the distance, and watched the fringes sharpen, each luminous stripe separated by a shadowed interval. The observers leaned closer, tracing the regular spacing with their eyes, then with careful measurements. Young spread his notes beside the screen, sketching the pattern as a series of alternating crests and hollows. He spoke of waves extending from each side of the card, their paths differing by whole or half wavelengths, combining in some regions and cancelling in others. He wrote of coherent beams that maintained a steady relation, like synchronized ripples crossing on a pond. Around him, the familiar Newtonian particles seemed to falter, replaced by something that bent, blended, and interfered with itself. In lecture halls and observatories across Europe, the conviction that light moved as a continuous wave in an all-pervading medium settled into routine practice. Textbooks displayed Young's fringes and Fresnel's integrals beside Poisson's spot, no longer as curiosities, but as standard proofs. New instruments relied on interference for ever finer measurements. Tiny shifts in bright and dark bands revealed small changes in length, temperature, and refractive index, turning once paradoxical patterns into precision tools. Engineers and physicists treated the luminiferous ether as calmly as they treated steel rails or glass lenses. It seemed to fill every void, allowing light waves to cross interplanetary space the way ripples crossed a pond. As spectroscopes spread through laboratories, prismatic colours from heated gases and stars appeared as signatures of distant matter. Each sharp spectral line implied a stable wave frequency in the ether, suggesting hidden regularity in atoms and in the structure of the medium itself. With this new confidence, investigators began to ask how fast the Earth ploughed through the ether, and how that motion might subtly distort measured speeds of light. The success of wave theory invited exacting tests rather than doubt. Interference, once used to disprove corpuscles, now served to probe the supposed stationary medium. As the century advanced, more elaborate arrangements of mirrors, beams, and paths were planned, seeking the tiny optical traces of the planet's silent rush through space. Across textbooks and lecture halls, light had been treated as a wave, and waves seemed to demand a medium. Sound had travelled through vibrating air, and water waves had rippled across liquid surfaces. By the same reasoning, light appeared to require something to tremble within. Physicists described a substance that filled every gap between atoms and stretched between the stars, weightless yet ever present. It slipped through glass, metal, and stone without friction, remaining invisible and undetectable by ordinary means. This imagined substance, the luminiferous ether, had been mapped with meticulous care. William Thomson, later known as Lord Kelvin, and others sketched diagrams in which tiny elastic structures threaded all of space, straining and rebounding as light waves raced past. George Stokes and his contemporaries proposed mechanical models that assigned the ether almost contradictory traits. It had to be stiff enough to transmit the unimaginably rapid vibrations of light, yet so fluid that planets glided through it without heating or slowing. In Victorian laboratories, ether diagrams had hung beside planetary orbits and electrical circuits, woven into lectures and calculations that shaped professional lives. Blackboards showed Earth orbiting the Sun, ploughing through what many regarded as a stationary, universal ether. If that rigid-seeming medium truly stood still in space, Earth's motion should have stirred up a steady ether wind. That wind, drifting past the planet like air past a moving train, ought to have nudged the speed of light differently along different directions. The heavy stone pier stood cool and unmoving, while the interferometer drifted almost frictionless on its circular bath of mercury. Gas lamps and sunlight from a high window flashed faintly from polished brass, glass plates, and distant mirrors. A narrow beam of white light entered the apparatus, struck a half-silvered plate, and divided. One ghostly ray ran the length of one arm, the other slid off at a right angle, each racing toward a mirror fixed at equal distance. Both beams returned to the central plate and overlapped, etching sharp, parallel interference fringes into the eyepiece field. The pattern trembled at the slightest vibration, so footsteps were hushed and distant wagon rumbles were watched like disturbances in a seismograph. The apparatus turned slowly on its mercury pool, marking out new orientations with respect to Earth's motion through the ether, while readings of fringe positions, times, and temperatures accumulated in notebooks beside the instrument. Calculation sheets lay scattered with carefully penciled expectations, a shift of a fraction of a fringe here, another small displacement there, all predicted from Earth's orbital speed through the supposed ether wind. The sensitivity of the instrument exceeded these requirements. Every known correction, from thermal expansion to local air currents, had been considered. Yet rotation after rotation, day after day and season after season yielded almost no systematic shift at all, leaving the once indispensable ether without measurable trace. In laboratories and lecture halls, the absence of an ether wind spread as an uncomfortable fact rather than a triumph. Letters carried diagrams of interferometers and long columns of figures, each author convinced that some overlooked motion or hidden vibration still waited in the apparatus. At conferences, polished calculations shared space with quiet unease. The ether had woven together optics and mechanics for decades. To discard it now seemed like tearing fabric from the heart of physics. Hendrik Lorentz and George Fitzgerald pursued a more delicate repair. They calculated how a rod moving through the ether might physically shrink along its path just enough to erase the expected fringe shift. Chalk dust traced symbols that became the Lorentz-Fitzgerald contraction, turning each measuring stick into a suspect witness altered by its motion. On paper, the ether survived, but only by demanding that space itself quietly reshaped objects to conceal their flight. Other researchers searched for refuge in motion itself, imagining the Earth dragging the ether along as it travelled. Much as moving water in Fizeau's experiment partly carried light, they adjusted velocities and refractive indices, hoping for a scheme that matched every observation. None fit. Replications by Morley and Dayton Miller, and careful variations across Europe, kept returning the same result. No detectable drift, no whisper of a cosmic medium, only an unnerving stillness where resistance had been expected. In a cramped office above the streets of Bern, a young clerk sat surrounded by patent applications and stacks of paper. Between routine technical descriptions, he returned to a single disturbing fact. Light appeared to move at the same speed, no matter how the source or observer moved. The Michelson-Morley result no longer looked like an experimental mishap. It suggested that motion through an invisible ether had never existed, and that something deeper governed light and movement. He proposed two simple statements. First, every observer moving at constant velocity experienced the same laws of physics. Second, light in a vacuum travelled at a fixed speed for all such observers. A thought experiment placed a clock built from a beam of light on a fast-moving train. To someone on the ground, the light traced a longer diagonal path between mirrors, yet still moved at the same speed, forcing the time between ticks to stretch for the moving clock. Another imagined network of clocks stretched along a railway line. Signals of light synchronized them for one observer, but for someone rushing past, the signals reached different clocks at different moments. Events that had been simultaneous in one frame no longer aligned in another. The equations of time dilation and length contraction followed from keeping light speed fixed, not from rescuing an ether. Time, distance, and simultaneity dissolved into a single, intertwined space-time. In a quiet laboratory at Bell Labs in 1927, a beam of electrons met a carefully prepared nickel crystal. Vacuum pumps hummed, gauges flickered, and technicians adjusted voltages that guided the invisible stream. When the scattered electrons struck a detector, their counts traced peaks and troughs that matched the patterns known from X-ray diffraction. The data aligned with Louis de Broglie's proposal that matter possessed a wavelength, turning electrons into participants in a wave experiment. Recreated setups showed electrons fired one by one towards slits and crystals, each impact appearing as a solitary dot on fluorescent screens or electronic detectors. At first, the emerging pattern looked random, a speckled field of isolated events. As more electrons arrived, bands quietly emerged where earlier there had been only scattered points. The distances between bright and dark regions agreed with wave equations, even though every recorded mark remained the footprint of a single, localized, particle-like event. Later experiments repeated the procedure with neutrons and atoms, then with large molecules such as Buckminster fullerene, Cs60 in 1999. Heavy, complex structures drifted through double-slit apparatuses in carefully shielded vacuum chambers. Detectors logged single hits from each molecule, yet over hours, the same striped interference pattern slowly assembled itself. Larger organic molecules followed, carrying dozens of atoms, and still they produced wave-like fringes. Common experience with solid objects offered no image that matched these accumulating, precisely measured results. In quiet laboratories, beams of electrons and photons still passed through two narrow slits, yet now every detail of the apparatus was questioned. Physicists placed tiny detectors beside each opening, devices sensitive enough to register the faintest quantum tap. When the detectors recorded which slit each particle used, the familiar interference fringes vanished from the screen. The pattern hardened into two broad bands, as if solid pellets had simply chosen a side and flown straight through. When the detectors were removed, or coupled so weakly that no reliable path record could be kept, the fringes returned. Long exposure photographs showed bright and dark stripes rebuilding themselves, dot by dot, from countless individual impacts. Nothing in the source had changed. Nothing in the slit's geometry had moved. Only the possibility of knowing the path had altered. The particles behaved like waves when the paths stayed indistinguishable, and like localized objects when the paths became distinguishable. Later experiments pressed this dependence on information even further. In the late 1970s and early 1990s, physicists used sophisticated which-way markers and quantum erasers that tagged or erased path information after a particle had already passed the slits. The final statistics on the detection screen shifted accordingly. Whenever the paths could in principle be told apart, interference disappeared. Whenever that information was scrambled beyond recovery, fringes reappeared. Microscopic reality revealed itself as a network of possibilities, solidifying only through acts of measurement. Brass tubes, oil lamps, and floating stone tables had once defined the frontier of precision. In a quiet Cleveland basement, light had raced back and forth along Michelson's interferometer, its fringes refusing to betray any drift through an invisible ether. On a different bench, narrow slits cut into metal plates had scattered electrons and photons into delicate bands. These arrangements of mirrors and slits appeared simple, yet their patterns quietly undermined familiar ideas of space, time, and matter. Decades later, the same principles spread across laboratories and observatories. Laser interferometers stretched for kilometers, like LIGO, listened for ripples in space-time from colliding black holes, their sensitivity built on Michelson's design. Arrays of stabilized lasers and optical cavities disciplined atomic clocks, setting global time and testing relativity in Earth's orbit. At smaller scales, refined slit and interferometer experiments steered single photons and atoms, revealing entanglement, delayed choices, and correlations that defied classical expectations. Everyday habits had suggested that time flowed identically everywhere, that objects possessed definite properties regardless of observation, and that causes advanced in a tidy line. The records from these interferometers and slits told a different story. Simultaneity depended on motion, lengths shortened at high speeds, and particles formed interference patterns until measurements forced specific results. Richard Feynman had pointed to the double-slit as the essential quantum mystery, while Albert Einstein acknowledged that relativity reshaped the very meaning of time, showing how modest apparatuses had widened the boundaries of reality itself.